Hello. So we start today with the next chapter, namely determinants, the basic theory of determinants. Determinants is a very vast story. There are many books written on, fat books written exclusively on determinants. We can't touch upon everything. We'll just touch upon the most basic notions of the theory of determinants. So first of all, let's begin with the setup. A is a n cross n square matrix, and the columns are C1A, C2A, Cna, or C1 of A, C2 of A, Cn of A, or simply C1, C2, Cn are the columns of A. Instead of thinking of A as a n cross n square array, we may think of it as an ordered n tuple of columns C1, C2, Cn. A square matrix can be thought of as an ordered n tuple of columns C1, C2, Cn, namely an element of Rn cross dot 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 cross Rn, but n factors, Cartesian product of n copies of Rn, and you take an element of that, you get a n columns. Each column has n entries, and so it's a n cross n matrix. So now the set of all n cross n matrices can be thought of as the same, can be regarded as Rn cross Rn n factors. So what is the determinant? Determinant is a very specific function that assigns to each matrix a square matrix. Each square matrix, in this entire lecture, we are only going to be concerned mostly with square matrices. Determinant is different only for square matrices. So we're going to assign to each square matrix a real number. You have come across this concept in standard 12. But we shall arrive at those expansions that you saw in standard 12 in a more natural way through some specific properties of this function. It's a very, very specific function, and this function is required to possess certain properties. Sometimes we'll provide an argument for 3 by 3 matrices, but in most cases, in such cases, it will be clear how the general case should proceed. Okay, so definition. The determinant function, or dit function, is the function f from Rn cross dot 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 Rn to R, n copies of Rn, satisfying the following properties. When I input the standard unit vectors in that order, E1 cap, comma, E2 cap, comma, dot 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 En cap, it should give me the value 1. This is called the normalization property. The second property is called skew symmetry. If I switch the position of two columns, the value of the function must change sign. I put a negative sign there, specifically marked in red, and I'm calling it skew symmetry. If I switch any two columns, any two inputs, if I switch their positions, the value of the function must become negative. It should pick a negative sign. Multilinearity. Multilinearity simply means that it is linear in each input. Okay, so for example, if I replace the first column, instead of C1, if I take alpha C1 prime plus beta C2 prime and keep the other columns intact, C2, C3, Cn, then the value of the function will become alpha times f of C1 prime, comma C2 dot 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 Cn, plus beta times f of C1 double prime C2 dot 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 Cn. So this is linearity with respect to the first variable. Well, if I just put this requirement, it will all automatically follow that it will be linear with respect to the second variable, third variable, fourth variable. Why? Because the previous property. I can switch two of the columns and the value simply changes sign. So linearity with respect to the first column will mean linearity with respect to the second column, because if I replace C2 by alpha C2 prime plus beta C2 double prime, and then I keep C1 intact, C1, C3, Cn intact, then what I will do is I'll first switch the second column of the first column, use linearity with respect to the first argument, and switch back when the job is done. So I leave it to you to think about this. It's a very, very easy conclusion that you will draw. If I postulate linearity with respect to the first input, it will automatically follow that a similar thing should hold for C2, C3, one at a time. all n minus 1 inputs should be the same, and only one of the inputs should become, so one of the inputs, say ck, becomes alpha ck prime plus beta ck double prime. Then this, I mean, in 12th standard, you say that if a column is a sum of two columns, if a column is a sum of two columns, then the determinant is a sum of the corresponding two determinants. That's the way you express this law in standard 12. But here we are not saying that this function is a determinant. This is any function which satisfies this property. But obviously, how do you know that there is only one function which satisfies these three properties? Why am I calling it the determinant function? What is the reason for using the definite article here, not the indefinite article? So let's see. Before I answer that question, instead of taking alpha c1 prime, suppose I take beta to be 0. Suppose I take beta to be 0 and c1 prime to be c1 itself. Then what does it read? This particular thing reads f of c1 c2 f of c1 c2 cn equal to alpha times f of c1 c2 cn. That is, if one of the entries is multiplied by alpha, the effect is to multiply the value of the determinant by alpha. Okay. So yeah. So here the exercise is, I have postulated linearity with respect to the first entry. Why should you have linearity with respect to the second entry? I already explained this to you. Okay, and then linearity with respect to the kth slot. Okay. So uniqueness, the use of the definite article, the in the definition should suggest that a function f that satisfies the properties 1, 2, 3. Which are these properties? Normalization, skew symmetry, and multilinearity. If a function satisfies these three properties, a function from where to where? A function from Rn cross dot 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 Rn, n copies of Rn, n columns in Rn, and the codomain or the target space is the real numbers. Okay, a function has this Rn cross Rn, n copies as domain and R as a codomain, and it satisfies the three properties of normalization, skew symmetry, and multilinearity. Then that function is unique. There's only one such function, and that function will be called the determinant. So it's a unique function which satisfies that property. The domain is exactly n tuples of columns in Rn, same n in both the places. Okay, please remember that. I encircled it in red. Proof is simple, and a little thought will convince you why such a thing must be unique. Let us look at the n equal to 3 case first. Let us look at, in fact, both existence and uniqueness will come out of the same logic. Let us try it for n equal to 3, and the general situation will become clear to you. So we are taking a function f, and its inputs are 3 column vectors v1, v2, v3. But the v1 can be written as a11 e1 cap plus a21 e2 cap plus a31 e3 cap. So let us just write v1 in terms of the standard unit vectors in R3. Keep v2 and v3 intact for now. So what will be multilinearity? Multilinearity will say that a11 times f of e1 cap v2 v3 plus a21 times f of e2 cap v2 v3 plus a31 f of e3 cap v2 v3. And let us use sigma notation. Sigma summation I from 1 to 3 ai1 f of ei cap v2 v3. Now let us put in v2. v2 is a12 e1 cap plus a22 e2 cap plus a32 e3 cap. Again, use multilinearity in the second slot. Multilinearity in the second slot means what? Your first slot is e1 cap, that is main fix. Now e2, a12 e1 cap, the a12 will come out, ei cap e1 and v3, etc. So that's it. So what are you going to get? So again, using summation sign, it will become summation I from 1 to 3. The original summation was there. ai1 was already there originally. Now what you're going to have is that aj2, right? a12 will be there, a22 will be there, a32 will be there, aj2 f of ei cap ej cap v3. Finally, we must put v3. V3 will be A13, E1 cap, A23, E2 cap, A33, E3 cap. Put that in and again use multilinearity, this time in the third slot. Multilinearity, the third slot. You get one more summation. So 3 summation signs. IJK from 1 to 3, AI1, AJ2, AK3, F of EI cap, EJ cap, EK cap. So now we are left with computing. Now we are left with dealing with this F of EI cap, EJ cap, EK cap. I'm going to say that this F of EI cap, okay, before we get into this, suppose for example, if two of these indices are equal, suppose if what will be the value of F of E1 cap, third slot, let us say V3. Suppose if two slots are equal, what will be the value of the function? Remember that you got E1 cap. But if I switch the two columns, it's going to be the same. No? If I have put the two columns are E1 cap and E1 cap. So flipping it on the one hand will not give you anything new. But on the other hand, flipping it is supposed to produce a minus sign. So both must happen. F of E1 cap V must be equal to F of E1 cap V, because the two columns that you have swapped are identical columns. On the other hand, the swapping of the two columns should have produced a minus sign. So both must hold. F of E1 cap V must be equal to minus of F of E1 cap V. Only way that can happen is 0. F is 0. So in short, when two of the inputs are equal, the function must take the value 0. That is a property of skew symmetry. So now when you have this EI cap, EJ cap, EK cap, I may, without loss of generality, assume that IJK are distinct. Now remember that if IJK are distinct, that means that this ordered triple I, J, K is a permutation of 1, 2, 3. It is a permutation of 1, 2, 3. Now how do you get a permutation from 1, 2, 3? How do you rearrange 1, 2, 3? For example, what is the permutation of 1, 2, 3, 2, 1? 3, 2, 1 is a permutation of 1, 2, 3. 2, 1, 3 is another permutation of 1, 2, 3. How many permutations are there? 3 factorial. 6 permutations you have of 1, 2, 3. And so there are 6 different epsilon ijk's. Now epsilon ijk will be either 1 or minus 1. I'm going to call it the parity. Epsilon ijk will be 1 if the number of exchanges needed to bring EI cap, EJ cap, EK cap to E1 cap, E2 cap, E3 cap, or the number of inversions, the number of transpositions that I need to bring IJK to 1, 2, 3. So suppose, for example, I take the permutation 2, 1, 3. The 3 is already in the right position. 3 is the third position. So I just have to switch the first and the second. 2, 1 has to become 1, 2. So the number of transposition needed to bring 2, 1, 3 into the standard position 1, 2, 3 is 1. And so epsilon ijk will be, and this 1 is an odd number, so epsilon ijk will be minus 1. So it is a parity, odd number and even number. If it is an odd number, the value of epsilon will be minus 1. If it is an even number, the value of epsilon will be plus 1. So for 2, 1, 3, since one transposition was required, it's an odd permutation. The parity is odd, so the value of epsilon will be minus 1. What about 3, 2, 1? What about 3, 2, 1? Again, 2 is in the right position. 2 is in the middle position. So one swap between 3 and 1. Odd permutation. What about 3, 1, 2? 3, 1, 2. Look at the permutation 3, 1, 2. 3 first, 1 next, and 2 last. First, I have to swap 3 and 1, right? So 3, 1, 2 will become 1, 3, 2. After that, I have to swap 3 and 2. So that's it. 2 exchanges are required to bring 3, 1, 2 to 1, 2, 3. And that parity, and 2 is an even number. And so the value of epsilon will be plus 1. So epsilon 3, 1, 2 will take the value 1. And epsilon 3, 2, 1 will take the value minus 1. I hope this matter is becoming clear. Okay, so if two of the arguments are equal, the value is 0. Now, since now let us make a convention that epsilon ijk will be 0 if two of the arguments are the same. That's a convention that we make. So basically, what are we having? This particular f of ei cap, ej cap, ek cap is simply epsilon ijk. So the function f of v1, v2, v3 has been completely determined. In other words, the fate of the function now is completely sealed. There is no other choice for f. If I demand that f must be multilinear, skew symmetric, and normal, that is, if it takes the value 1 at e1 cap, e2 cap, e3 cap, then the fate of the function is sealed. It is this function only. This is the function star. So not only we get uniqueness, we also get existence. Namely, the right hand side is the function which satisfies this property by construction. So we have arrived at both the existence and it. So the function, the determinant, so this theorem says that there's a unique function. There's a unique function from R3 cross R3 cross R3 to R, which satisfies f of e1 cap, e2 cap, e3 cap is 1. F switches sign when two of the arguments are flipped, and it should be multilinear. It should be multilinear. So such a function is the determinant function. And what is the determinant function? And that determinant function is displayed here. So for example, an ijk, the sum will be over distinct ijk's, because if two of the indices are equal, this epsilon is assigned the value 0. So suppose, for example, I is 1, j is 2, and k is 3. Then the number of transposition needed to bring 1, 2, 3 to 1, 2, 3 is 0. I don't have to make any transposition. 0 is an even number. 2, 1, 3. 3 is already in the right position. One swap has to be made. So 1 is an odd number. So epsilon 2, 1, 3 is minus 1. 1, 3, 2. 1 is already in the right position. Only 3 and 2 have to be switched. Again odd. 3, 2, 1. 2 is already in the right position. 1 and 3 have to be swapped. 2, 3, 1 and 3, 1, 2. Two transpositions are required to bring it to the right, to bring it to 1, 2, 3. And so 2 is an even number. So epsilon value is 1. So I can completely write out this 6 terms in this expansion, and 3 of those terms will appear with the plus sign, and 3 of the terms will appear with the minus sign. So this is the determinant of the 3 by 3 matrix is A11, A22, A33 plus A21, A32, A13, A31, A12, A23. 3 with minus signs, A11, A32, A23, minus A31, A22, A13, minus A21, A12, A33. You just have to look at, this has been written, this object has been written out. So I take I equal to 1, j equal to 1, k equal to 1, and then I look at all possible ijk's, all possible permutations that you put in, and you put in the appropriate sign, and you get this. Does this look familiar? It probably looks familiar to the expansion of a 3 by 3 determinant that you did in your 12th standard courses. All right. For n by n matrices, the procedure is going to be quite similar. If two of the arguments are equal, then the determinant will be 0. Then the function will be 0. And then again, you'll do the same thing, whatever you did here, but with n arguments, v1, v2, vn. And then first you'll write v1 as a11, e1 cap, a21, e2 cap, an1, en cap. So many terms will be there, and then will be one summation, and then there'll be next summation, and there'll be next summation, and so on. And you will be getting ultimately epsilon. You'll be down with this f of ei1 cap, ei2 cap, ein cap. That will be epsilon i1, i2, in times f of e1 cap, en cap. And this epsilon and this i1, i2, in is a permutation of 1 to n. And this permutation will be, the epsilon value will be minus 1. The number of transpositions required to bring it to the standard form is odd, and it will take the value 1 if the number of exchanges required is even. This number, and so this is the number of the odd parity of the permutation. And so what is the value? So what is the value of the determinant? The determinant will have how many terms? N factorial terms will be there in the determinant. It will be summation a summation A. What do you have here? Let us see again. A I1, A J2, A K3. Now, of course, I'll have n summation. So A I11, A I22, dot 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 A INN times epsilon I1 I2 dot 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 IN, where epsilon is the sign of the permutation. You'll have how many terms? You'll have as many terms of summation as there are number of permutations of 1, 2, 3, n. N factorial terms will be there in the general expansion. Correct? So this is the double star. So the function f from Rn cross dot 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 cross Rn to R, n copies of Rn, function of n variables, n inputs, each input is a vector in Rn, and the function satisfies the three conditions: normalization, skew symmetry, and multilinearity. Such a function, if it exists, such a function exists and is unique, and in fact is given by this double star. It is unique, it exists, and its fate is sealed. It's basically double star and nothing else. And the right hand side of double star is called the determinant of the matrix Aij. It's called the determinant of this matrix Aij. Okay, the determinant of Aij is called the right hand side of star. Okay. Now, I talked about the parity of a permutation, right? Odd permutation, even permutation, number of exchanges required. It's also known as the number of inversions present in the permutation. How do I calculate this number? One way to calculate this number is to compute this ratio. Your permutation is I1, I2, In. So do I1 minus I2, I1 minus I3, I1 minus I4, dot, 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 all the way up to In minus 1 minus In. Take all the differences. And then look at the corresponding differences and do the same thing with, compare it with the standard one, 1 to n. 1 minus 2, 1 minus 3, 1 minus 4, dot, 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 1 minus n, 2 minus 1, 2 minus 2, etc. So 2 minus 1, sorry, 2 minus 2 cannot be there, excuse me. So the differences, the n into n minus 1 by 2 differences you'll get. 1 minus 2, 1 minus 3, etc. 2 minus 3, 2 minus, excuse me. So 1 minus 2, 1 minus 3, dot, 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 1 minus n, 2 minus 3, 2 minus 4, etc. n minus 1 minus n. So you write these, you take the ratio of this and you get the number of inversions. You can check, you can use this formula for the number of inversions to check the correctness of these things that were written. That epsilon 213, epsilon 132, epsilon 321, etc. are giving you minus 1. Epsilon 231 and epsilon 312 are giving you plus 1. You can check the correctness of this. So my general advice will be, don't use this formula. It's highly cumbersome and you will make mistakes. What I suggest is that you take a specific permutation. 5, 2, 3, 1, 4. How do you bring 5, 2, 3, 1, 4 to 1, 2, 3, 4, 5? You want to bring 5, 2, 3, 1, 4 to 1, 2, 3. First of all, 5 has to go to the very end, right? First of all, 5 has to go to the very end. So let us switch the position of 5 and 1. Let us switch the position of 5 and 1. What do you get? Keep a piece of paper with you ready. You get 1, 2, 3, 5, 4. One transposition I made. I switched the position of what? I switched the position of 5 and 1. Now I need to do one more transposition. No. 1, 2, 3 are the correct positions. 4 is not in the right position. So switch 4 and 5. You get 1, 2, 3, 4, 5. Finished. So how many transpositions have I used? 2 transpositions. So this particular 5, 2, 3, 1, 4 is an even permutation, or epsilon 5, 2, 3, 1, 4 takes the value 1. I would like you to do this permutation of the nine numbers. Okay, try this as an exercise, and you will notice one thing, that one question would have occurred to you, namely, suppose somebody does this. I mean, suppose somebody could say, okay, first I will switch 5 and 2, and then I'll switch, and then I'll do successive transposition. I'll bring 5 to the extreme end, and then I'll keep doing it. You'll use larger number of transpositions. But no, in other words, somebody could do this flipping. We did this flipping in 2 ways. Somebody else may try it and get it in some other way. They may need more transpositions, but the parity will be the same. The number of transpositions that is needed to take it to the standard form 1, 2, 3, 4, 5 may be different. Different people may do it differently and they may arrive at different numbers, but the parity will be the same. All of them will be even or all of them will be odd. That is the most remarkable feature. And so though the number of transpositions is not unique, the parity of the number of transpositions is unique. So the epsilon is a very well-defined function. There's no problem. So basically, what is happening? The determinant, the determinant of the matrix is a polynomial, is a certain very, very special polynomial in the entries of the matrix, correct? So the determinant is a polynomial function. It's a very nice function, but this polynomial function has certain very remarkable properties. The entire expression is a polynomial in the symbols a11, a12, etc. Now the question when you see a polynomial, you want to know whether this polynomial, is it a reducible polynomial or an irreducible polynomial? Will it factorize, for example, into two non-trivial factors? Answer is no. This is going to be an irreducible polynomial. And how do you prove that it is irreducible? It's quite a non-trivial question. We shall not be able to answer that question here. But it's not difficult or anything like that. It's just that it's not germane to this course. So we cannot be doing this here. But for n equal to 2, what is the determinant? A11, A22 minus A12, A21. That you can easily decide whether it factorizes or not. I think we'll stop this capsule 7a here.